Welcome to Math 31. This is an exercise on rates of change questions. Nothing really new here, but just looking at some applications, non-motion related applications of rates of change. Now this first one, I decided to do it last lesson, so I'm going to just go to the next one. But it'll be just kind of a grab bag, an assortment of problems. So here's where I want to start. So we get the average cost to produce an object is given by this formula. C is equal to 0.02x plus 30 plus 1800 over x, noting that x has to be greater than or equal to 0. If you paid even more attention, even though that's the domain, you might also be aware, well, x cannot be equal to 0 according to this formula. So fair enough. So we'd have to put that additional restriction on if it becomes an issue. And then this goes on to say where C is the average cost and x is the number of units produced. So with this formula, if we were to plug in any x value, it would give us the average cost. So if you produced one object, x equal 1, the average cost, would be whatever. Now, as x goes up, as it increases, we would then, just using sort of simple reasoning, would assume that the C value the average cost would go down. What we're trying to do with this problem, at least for the first question, would be how many units should we produce to attain a minimum cost? And then part B is what is the minimum cost? Now this particular question, you'll see, doesn't really fit in with the ones that we did previously, nor does it really fit in totally with the ones that we're going to be doing in the next little while. But it should also make sense. When we're looking for a minimum cost, it means that the derivative is going to be set equal to 0 because it's a turning point. So if you think back to some of the basic graphing that we did before when we were looking, say, for a vertex, you do it in Math 20 as well, where the derivative is equal to 0 represents a turning point. So it's either going to be a minimum or a maximum. So make a little note. So where is the derivative equal to 0? So that would be its maximum value or its minimum value. So if you were to graph it, you could probably solve it that way. And then B, what is the minimum cost? Well, to get the answer to this one, we would have to be using the original formula because that formula is giving you the cost per unit item. So it all starts by noting that the formula, the equation, C is a function of x, if you want to write it in that form, is 0.02x plus 30 plus 1800 x to the negative 1. So we need to write it like that. And we want C prime at x, or if you want to use Leibniz notation, would be the derivative of C with respect to the x variable. So C prime x, I'm going to use this form, would be equal to 0.02. The 30, the derivative of 30, of course, is 0. And then minus 1800 x to the negative 2. So therefore, C prime at x is equal to 0.02 minus 1800 over x squared. Reason I wrote it like that is because now I'm going to have to solve this equation, and I want it to have the positive exponent just to make it a little bit easier to solve. So I'll bring up a new screen, get some space to work this one out, and here is the question again. Where is C prime at x equal to 0? Because that's going to represent a turning point on the graph. This is a slightly oversimplified way to look at this because when we get into the real extrema max-min questions, we have to pay a little more attention to things, but it still is correct, i.e. min or a max. So the derivative goes up, and then it goes down. So 0 is equal to 0.02 minus 1800 over x squared. And to solve this one, to make it easier, I'll take that negative term to the left side. So 1800 over x squared is equal to 0.02. And if I now multiply both sides by x squared, I'll get 0.02 x squared is equal to 1800. Math is fairly simple. Divide by 0.02. You're going to get a big number. X squared is equal to 90,000. Now when we take the square root, we'll get 300, plus or minus, but we can only keep the positive answer. So x equal positive 300. So therefore, for question A, 300 units should be produced to minimize the cost. Or minimize average cost. Now some of you are thinking, well, how do we know that that is actually a min and not a max? Because the turning point could be either. And that's a reasonable question. And as I said, I am oversimplifying this question. This is the minimum. We are right with it. But we will have to pay a little more attention to issues like that when we get into the real, hardcore max-min. Now for question B, we want to find out, well, what is the minimum cost, minimum average cost? So we use the original. So we want to get C at 300. Because we know that x equal 300 will minimize the average cost, so by plugging back into this formula, we can find out what the average cost will be. So 0.02 times 300 plus 30, and then plus 1800. I'll just have to write this down below, over 300. So just run that through your calculator, or work it out by hand. 0.02 times 300 plus 30 plus 1800 divided by 300, which is going to be 6. And I'm getting C at 300 is equal to 42. So the cost, the average cost, is 42. I will call this dollars, even though the question didn't say so, at its minimum. Probably could have worded that a little bit better, but that's got the idea there. So once again with these, it's recognizing which equation that you're working with, the derivative, first derivative, second derivative, or original. Next question is the estimated number of houses in New Norway after T months is given by n at t is equal to 1000 t over 14 plus t. We want to find the rate of change of the number of houses after 6 months. Now this is actually a more normal question than the previous one, at least for this section that we're working on, this unit, because it's measuring a rate of change with respect to time, which is typically what we're going to be doing. So the original equation is telling us what the number of houses are. So if you plugged in t is equal to 0 to that original, it would tell you how many houses there are in New Norway. Interestingly, you'll get 0. which would mean that there probably is a domain on this one that we'd have to pay attention to if we were interested in that. But really what we want is the rate of change of the number of houses after 6 months. So at t is equal to 6 months, at what rate of growth or decrease are we experiencing? So it won't be the number of houses, it would be the number of houses per month. But it all starts the same way. We want to find the rate of change with respect to time in months. So this could be either expressed as dn dt, which is more accurate. It was given, or it gives more information, or n prime at t, because that would mean the same thing. In this case, you were given the function notation. So we go on with this little problem. It isn't going to be that bad of one to solve. I will use the quotient rule. So u is equal to 1000 t. So I'll write that as u prime is equal to 1000. V is equal to 14 plus t. So v prime is equal to 1. And y prime, using the quotient rule, is equal to u prime v minus u v prime over v squared. So n prime at t is equal to 1000 times v, which is 14 plus t, minus u, which is 1000 t times 1, so 1 times 1000 t, all over v squared, which is 14 plus t squared. N prime at t then is equal to 14,000 plus 1000 t minus 1000 t over 14 plus t squared. This will give us n prime at t. 1000 t's cancel and we get 14,000 over 14 plus t squared. And we want the rate of change at t is equal to 6. So n prime at 6 is equal to 14,000 over 14 plus 6 all squared. So 14,000 divided by 20 squared, and we will get the rate of change is 35 houses per month. Anybody who's been to New Norway recently might challenge those figures, but this is what we're getting. So, next question, kind of the same sort of thing. So, stop me if you want and go through this one. But here we're given population of this town, that's Jablib, Wisconsin. P at t is equal to 10 times 6t plus 9 over 3t plus 7. T is given to us as the time in years since 1955. So this formula will allow us to get the population at any given time since 55. What we want is the rate of change of the population in 1986. So not dealing with the population itself, but at what rate is it changing? So in this case, how many thousands per year? So to get an answer for this one, we have to differentiate this with respect to time. But the way this equation is given to us confuses us perhaps a little bit because of the way that 10 is written outside. Now you can do this a number of ways, and most people would probably fumble through it just fine. But I'm going to take that 10 and multiply it in to the fraction. Now remember, the 10 would only be multiplied by the numerator. So it's 60t because it's 10 over 1. So 60t plus 90 over top of 3t plus 7. So here we are with a quotient rule once again. U is equal to 60t plus 90. So U prime is equal to 60. V is equal to 3t plus 7. So V prime is equal to 3. So Y prime, as we know, with the quotient rule, is U prime V minus U V prime over V squared. So P prime as a function of t is equal to 60 times 3t plus 7 minus V prime of 3 times 60t plus 90 all over top of V squared, which is 3t plus 7 squared. So P prime at t is equal to 180t plus 420 minus 180t plus 270 all over 3t plus 7 squared. So before I bring up the screen, I will simplify this expression as far as I can. Make sure I've got all this thing. Oops, look at that. That should be a minus 270. So don't. So minus 180t minus 270 makes a little more sense. The 180s go away. The 420 minus 270 should give us 150 over 3t plus 7 squared. Now, the next observation we have to make is 1986. So T is time and year since 1955. So we want to find P prime, the rate of change, for 31 years. So P prime at 31 is equal to, let me just say we want, and then I'll bring up a new screen. So be careful with that one. So bring up the new screen. P prime at 31, we substituted in, is equal to 150 over top of 3 times 31 plus 7 to the exponent of 2. So be careful with this one. I'm just going to drive it through the calculator. 150 divided by, open that bracket, 3 times 31 plus 7, close that bracket, squared. It works out to a clean number. P prime at 31 is equal to 0.015 thousandths per year. Now, that's a kind of an awkward way to write it. So you could say the population increases by, if you multiply 0.015 by 1,000, you'll get by 15 per year in 1986. Now the next question is going to be the messiest of them all, but it's kind of interesting. It may strike you as not a particularly useful application, but nevertheless the math is worth looking at. These are the lengths of the sides of a rectangle. A is this, B is that. We want to find the rate of change of area at t is equal to 64. So area is equal to length times width. So the area function as a function of time would be equal to 1, the one side, 1 plus t to the 1/3 cubed, times the other, which is 10 minus t to the 1/2 squared. And this is going to involve the product rule as well as the chain rule, but principally the product rule. So I take my u is equal to 1 plus t to the 1/3 cubed, and I'm note that u prime is equal to 3. So I write this as u prime, but in my mind I know that I'm taking the derivative of this function with respect to t. But u prime is just a convenient way to write it. So 1 plus t to the 1/3 to the 2. Now the derivative of the inner, I'll do that immediately, is the derivative, well, the derivative of 1 is 0. The derivative of t to the 1/3 is 1/3 t to the negative 2/3. And then when you multiply out those coefficients, 3 times 1/3 is 1, you'll get t to the negative 2/3 multiplied by 1 plus t to the 1/3 squared. And then I do the same thing for v, or a similar thing. V is equal to 10 minus t to the 1/2 squared. So v prime is equal to 2 times 10 minus t to the 1/2 to the 1 multiplied by the derivative of the inner. Derivative of 10 is 0, but the derivative of minus t to the 1/2, it becomes minus 1/2 t to the negative 1/2. And then v prime is equal to, the 2 times negative 1/2 will cancel, but we have a negative t to the negative 1/2, bringing that to the front, multiplied by 10 minus t to the 1/2. You could, of course, distribute that negative t to the negative 1/2 in. Actually works out nicely, giving you a very clean number, but I'm not going to. Instead, I'm just going to go back into the product rule and keep it the way it is, u prime v plus u v prime. The reason I'm not going to do an awful lot of work on this one is because I was given a number, and the t is equal to 64, so that's telling me that there's no real point to simplify this one extensively because I'm going to be substituting in. So as soon as I get this thing worked out, the soonest opportunity, I'm going to replace t with 64 and then turn it over to my calculator. So u prime v is going to give me, in fact, I'm going to bring up the new screen just to get some space, because she's going to take a little bit of room. A prime t is equal to u prime, which I've got to be t to the negative 2/3 multiplied by 1 plus t to the 1/3 to the 2. This gets multiplied by v, which is 10 minus t to the 1/2 squared, plus u times v prime. I'll put the v prime first because it's got the straggler term, so that's negative t to the negative 1/2 multiplied by 10 minus t to the 1/2 multiplied by u, which is 1 plus t to the 1/3 to the exponent of 3. Now, hopefully I've got all that written down right. And don't simplify. Normally you would be factoring out the terms, but I'm not going to bother. I'm going to go a prime at 64 is equal to 64 to the negative 2/3 multiplied by 1 plus 64 to the 1/3 squared multiplied by 10 minus 64 to the 1/2 squared minus the plus or minus changes to a negative, 64 to the negative 1/2 multiplied by 10 minus 64 to the 1/2 multiplied by 1 plus 64 to the 1/3 cubed. Now I know you're thinking out there, why not just punch it into your calculator now? And you can. In fact, it's a fine way to do it. I'm going to work out each term individually and then multiply, but that's just my preference. 64 to the negative 2/3 is 1 over 64 to the 2/3. And the cube root of 64 is 4. 4 squared is 16. So this whole thing turns into 1 over 16 multiplied by 1 plus 64 to the 1/3 is the cube root of 64. You can use your calculator, just know that. It's going to be 4, and then all this squared. Next bracket is 10 minus the square root of 64, which is 8, which is all squared. 64 to the negative 1/2 is 1 over the square root of 64, so 1 over 8, multiplied by 10 minus 64 to the 1/2 is 8, multiplied by 1 plus cube root of 64 is 4 again cubed. So I'm doing a low-tech way of working this solution out. So 1 over 16 times 5 squared is 25, multiplied by 2 squared is 4, minus 1 over 8 times 10 minus 8 is 2, multiplied by 5 to the 3. So the 1 over 16 and the 4, well, that'll simplify. So that's 25 over 4, minus, here the 2 divided by 2 is 1, divided by 2 is 4, and we get 5 cubed is 125 over 4. Now if you subtract that, you don't even need a calculator, really. Got a common denominator for us already. It's negative 100 over 4, so it's negative 25. And the rate of change of the area is negative 25. So the area is decreasing by negative by I don't need to put the negative now by saying decreasing by 25 square units per time unit at t equals 64 units. So that's how these ones go. Got to be careful, but the advice there is don't simplify it if you see it's going to be a substitution. If it looks like it's going to be kind of a nasty simplification. Now the thing is, this one would have been, after simplifying it, of course it makes substitution easier, but you are throwing in those extra steps, so I chose not to in this case. So that's it for these. The next lesson will concentrate on related rates, which is probably the big deal for this unit, but this will help you through most questions up to that stage. So thank you for your time.